Hello, hope you can all hear me. Good afternoon, good evening, and welcome to SFPE Greater London webinar series. It's me, as always, Francesca, the president of the chapter, and today, together with my colleague Matt Bonner, we'll be hosting today's webinar. Before I introduce today's speaker, I will just do the usual housekeeping. So, as you might already know, we are the Greater London Student Chapter. We bring together students from universities all across London that study or are interested in fire safety science. If you want to know a bit more about us, you can visit our website where we have all our upcoming events and also recordings of our past webinars. If you want to follow us and you want to have updates from us, you can follow us on our social media, mostly on LinkedIn and or Twitter. We welcome today Chiara Bedon, who is a professor at the University of Trieste in northern Italy. She is also the editor-in-chief of the International Journal of Structural Glass and Advanced Materials. She completed her PhD, so once she was a PhD student like us at the University of Trieste, and her topic was on structural glass design issues. And today she will be talking about structural glass and the fire endurance of structural elements. This is a very new topic for us. We've not talked about glass as a structural material ever, so we're very excited to hear a bit more about this. Chiara teaches structural analysis at the University of Turin, which is, as a civil engineer, it's one of the most important courses that I've taken in my life, so very, very important course. And yeah, she's done a lot of great research on the topic of glass and its response to blast and fire. So I hope you will enjoy her talk and that you will have a lot of questions for her after the talk. As always, we'll leave 15-20 minutes at the end of the talk for questions. So if you have any questions about glass, she's the right person. So make sure to ask them using the Q&A function that you have on Microsoft Teams. So Chiara, if you're ready, please. First of all, yes, we can see you now.
Yeah. Okay. Thank you very much, Francesca and guys, for organizing this very special meeting. And thanks for asking me to talk about glass, because in few words, it is something that I had the opportunity to start working during my PhD. So we are talking more or less about 10 years ago. And at that age, it was something totally new for me because, as you know, it's not a constructional material that is taken into account in traditional courses and lectures. So starting from, let's say, this new topic and material, I had the opportunity to go inside some aspects of the structural behavior of this material. And then, let's say, I didn't never stop to work with it. So today I'm more than happy to show you some results of a research activity that you can imagine is something always going on. Because we are talking about not only, let's say, a new material for building applications, for structural applications, but also we are talking about a lot of loading and boundary conditions and design issues that need to be solved. So more or less, what I can say that my research activity is something that for sure is, let's say, suggested and guided by open challenges for design applications And my, let's say, biggest pleasure is that some of the topics from my PhD activity are also part of the Italian technical document, the guideline CNR 210, that we did publish also in the same period of my PhD. So something where I had the opportunity to contribute in the working team and also include part of research funding that at the time of PhD were mostly related on buckling phenomena for glass structures. Today, I will show you something totally different, something related again to structural glass, but with a focus on fire performances. And this is something that I'm taking care of at my department, but also with some colleagues that provided a big contribution to part of the results that you will see in a few minutes. And in particular, I want to express my thanks to my colleague, Professor Christian Lauter from Dresden University, because you will see in few slides some experimental results that were handled by him. So going on, let me introduce the material, but also the challenges that we are trying to solve at the stage of studies. As you know, if we talk about glass, we can have in mind something totally different of our daily life applications, moving from automotive solutions, food solutions, but also, for sure, windows and facades. So the same material, more or less, is used everywhere, we can say, and especially for the building sector, we have a lot of open issues that still need to be solved. The basic application of glass in buildings, you will understand that is a typical, let's say, vertical partition, a typical facade or wall, where we expect that glass panels could provide a physical separation of indoor and outdoor spaces. But if you look at this solution from a structural point of view, you could also recognize that to the same glass panels, we are also asking to provide, let's say, appropriate safety levels to people, because it is true that it is a physical barrier for indoor spaces, but at the same time, we expect that these glass panels could behave properly against wind pressure, crowd pressure, and let's say also impact. Very shortly, let me say something else about this material in buildings. Probably you know very well these examples or similar examples that I'm going to show you, because especially in the last 10 years, we did see an increasing number of applications of load-bearing structural glass members for totally different solutions, going to stairs, roofs, and let's say not only and no more only vertical partitions only. Another very nice example is this touristic attraction. So we are talking again about the same material, which is used for, let's say, a very particular or, let's say, interesting application where people is expected to experience falling down, let's say, more or less, experience at the top of this building in Chicago. So something where we can move from bridges, structures, and everywhere in the world, but keeping care that structural glass is in any case a very brittle material. So while we know that this material is not safe for daily life objects, you can understand that we cannot accept any kind of risk for buildings and load-bearing members. So here you can see some typical examples of fracture. This may derive from extreme design actions, but also from, let's say, other reasons that I will skip in this specific presentation. And for sure, you will probably have in mind something like this. So a lot of shards and fragments that are the first reason of risk for people, especially under impact. So this is everything to introduce this construction material from a simple mechanical point of view. In few words, we can say that we are talking about a linear elastic construction material with a very brittle behavior in tension. And so we are talking about a solution which is for sure not safe for building solutions, and that we typically design in terms of stress peaks and deflection limits. Something that in words seems very simple and basically related to linear elastic considerations, where, let's say, the first important parameter is for us the elastic modulus of glass. We're talking about 70 gigapascal like for aluminium, and the tensile resistance. Everything else, let's say, can be solved easily, even under different loading and boundary configurations. Here you have a summary of basic mechanical properties that we should keep into account for simple mechanical and structural design considerations. But we should also mention, before moving to fire, that we can take advantage of heating and cooling stages during the production phase, in which, okay, we know that the glass is very brittle in tension, but we can also improve its basic mechanical features. And so you will probably here talking about annealed glass, which is the basic solution in which the tensile resistance is in the order of 45 megapascal. We can apply a partial pre-stress stage and increase this tensile resistance up to 70 megapascal. And for sure, the best solution is the fully tempered glass solution, in which you can see that the tensile resistance is in the order of 3 times the simple annealed one. So this is everything we are able to manage more or less and adapt to different design considerations, even assuming that we will never use simple monolithic glass layers, but at least 2 bonded glass layers in which we can take advantage of viscoelastic bonding foils, able to provide, let's say, a very thick and for sure more safe cross-section for our structural applications. Our attention will be given in that case let's say, no anymore to glass shards and fragments, because we are using laminated SAFETY glass just for this goal. But for example, we should be aware that the bonding films are strongly sensitive to several conditions, like time loading, temperature, humidity, and let's say, in general, aging. In this chart, you can easily see what happens to the, let's say, elastic stiffness of our bonding layers. The typical solutions in use are PVB or centric glass. As a function of temperature, you can see that the nominal value in design conditions is strongly affected by external temperature, so operational temperature. But this is not the only influencing parameter. We will see that a combination of, let's say, unsafe operational conditions can affect the shear stiffness of these bonding foils. But more or less, we have the instruments and tools to take care of this aspect and design a structural glass at room temperature for most of the boundary conditions of interest. Well, we have still a problem when we talk about fire, for example, and when we talk about fire for, let's say, traditional glass. I mean, glass that we can use for load-bearing components in buildings, but and we know that is brittle in tension material, but has nothing to do with fire. This just introduce you the concept because, for example, maybe you have already experienced with that. You can find on the market also a special glass which is specifically proposed for fire applications. So more or less the same material with some modifications just to ensure a very slow temperature degradation and temperature distribution of the degradation in the thickness of glass. In most of the cases, you will see or you will need to take care about glass elements that are characterized by large dimensions but a very small thickness. So something that will represent the critical aspect for design considerations. For sure, you can bond together 2 or more glass layers. We can talk about 3, 4, or even 5 glass layers in a laminated section. But in any case, this thickness will be most probably very small compared to the total size. So why fire considerations and fire resistance discussion is important for this brittle in tension material? It is very important because of the intrinsic material properties. Just imagine that we are talking about load-bearing elements that we are able to design against mechanical loads, but in case of fire are asked to sustain a combination of mechanical loads and also heating exposure. So something that we can easily schematize with this graphical scheme on the left. So you can imagine that especially for out-of-plane bending, we are talking about load-bearing element characterized by big dimensions compared to a very small, very thin thickness, and not only exposed to mechanical loads, so bending and everything related, but also to heating on the same or on the other side, depending on the configuration. So where is the problem for traditional glass? The problem is not only related to very limited tensile resistance, as we did talk a few minutes ago, but also to the sensitivity of its elastic modulus to high temperature. In the figure on the right, you can see what I mean. For sure, you can see that there are several types of glass, but the traditional one we use for windows and building applications is the brown one. So I don't know, you see my mouse, but okay, the brown in the bottom region of the chart is our reference mechanical parameter. In few words, we start from 70 gigapascal in cold conditions, and you see a linear decrease of this elastic modulus with temperature. At around 650 or more or less 70 degrees, the final result and the final behavior of glass is something that you can easily see in the picture on the top left corner. So something that we cannot anymore describe as a linear elastic solid material, but something totally different with null residual stiffness and load-bearing capacity. So our problem is no more related to mechanical design issues only, as we did talk at the beginning of this presentation, but it's something that we should consider in terms of thermal and mechanical load-bearing performance of these structural elements. And the combination of these two aspects makes the problem, let's say, a bit difficult to solve. So part of the research studies that I'm showing today are taken from some published papers, but keep in mind that this research project is still ongoing, and so we need for sure additional efforts to find a final solution. In the literature, you can also find some examples of fire experiments on different glass solutions, in which you can see here a simple glass beam under in-plane bending and, let's say, heating exposure on the side. On the right picture, you can see the setup of a fire experiment carried out on a beam, again, under in-plane bending, with, let's say, the web made of glass and top and bottom regions made of timber, so a timber glass solution. And today, specifically, I will use the experimental feedback from these laminated glass beams under fire, just to show you some numerical tips. So if you need then some additional data and details, you can ask me, or you can find in this publication. Another important aspect, but today I will not talk about it, is let's say, the orientation of our thin glass members compared to mechanical loads and to fire. Why? Because we did talk about a small thickness compared to the global size, and you can see this aspect very easily from this example. We have a thickness composed of 3 glass layers for the laminated section, and okay, for sure it is very small compared to the total span. Under fire, this means that we can take advantage of measure bending axis for this composite section and the best performance parameters from the mechanical point of view. We will see that it is very important. Otherwise, what happens when we have, let's say, our glass element exposed to mechanical loads on the top, for example, and fire on the bottom? So a very thin thickness compared to the bending deformations that we expect to come from mechanical and thermal loads. For sure, the behavior will be totally different, and for sure you can expect that the performance and the capacity, the residual capacity especially, of this solution will be much lower than the in-plane bending solution. But okay, let's start introducing this first setup. We talk about a simply supported beam. You can see the schematic representation on the right, where we try to, let's say, explore the thermal mechanical response under fire and a given mechanical load on the top at the mid-span section. Something that well represents the experimental setup we did talk about in a few slides ago. So basically it's something that we expect very easy to solve, because we know the mechanical properties of materials. We know how to describe the fire spread and distribution in time. So what else do we need? You will see that it is not so simple to draw some general conclusions, especially because the fire performance of structural glass members, even for simple mechanical systems, can be very different compared to other constructional materials. So what we did try was to adapt conventional performance indicators and performance limits to these new material for buildings. In doing so, for sure, we didn't need to introduce an insulation layer. So the layer that you see in yellow color, just to protect the region of boundaries and focus at this stage on the, let's say, central portion of the beam, which was directly exposed to fire. And through the parametric study, we did explore the in-plane bending response under a combination of mechanical loads and heating exposure. And we did also try to change the mechanical properties of the resistance cross-section, moving from the monolithic one to the laminated solution with 2, 4, or up to 6 glass layers, just to check the effect of these geometrical variations. As I told you, we did take into account some performance indicators that are typical of, let's say, beams, structural beams under fire conditions. So the deformation rate, and in this specific case, we did take care of maximum stresses in the glass elements, just to check the worst combination of mechanical and thermal loads in terms of possible fracture or melting of the material. Because on one side, we are talking about a structural material which we know is characterized by a tensile brittle behavior in tension. So at failure, for us, glass cracks in shards. But this is not true in fire conditions. So where do we move, or which direction do we take when we talk about fire performance and capacity of these members? Everything was carried out in this presentation, in this study, with the support of three-dimensional numerical models, in which we did explore the combination of thermal effects and mechanical effects. So something able to include the effects of Young modulus degradation with temperature, and everything related to this material modification with time of analysis and temperature due to fire. And here you see more in detail the experimental setup and the experimental behavior that I was talking about. So 3 layers of glass in a simply supported setup under a mechanical load at the mid-span section. You can see in these pictures, or from the link with more extended discussion, the typical behavior that was experimentally observed. We are talking about glass layers that are sensitive to temperature increase, but also of bonding layers, the interlayers, which are for sure even more sensitive to temperature. And you can see this degradation in the form of bubbles and white regions in the thickness. For the numerical study, we did take advantage of the experiments on 4 size beams, but also of some literature data related to material properties. First of all, the Young modulus and its sensitivity to temperature, but also some important parameters that usually we can skip for mechanical considerations in cold conditions. So the variation with temperature of specific heat, thermal conductivity, linear thermal expansion, and density. Everything was used as a basic input to study the deflection trend and deflection rate trend of these simply supported beams under a combination of sustained mechanical loads and heating from the bottom. Here you can see the first stage of validation, where the black dots are representative of the numerical model carried out in Albacus, while the other curves are representative of the full-size experiments. For sure, you can see some scatter at the final stage of bending response, but you can also see that for most of the fire exposure, and we are talking at least about 40 minutes of fire exposure, the match was very good in terms of deflection in time. And so this means that the modification of bending stiffness for this composite section was properly taken into account with the basic input parameters for material. If we look more in detail to the fire performance of these beams, what happens in fact? It happens that the configuration is totally different from our design bending considerations in cold conditions. So just imagine what happens if you take the beam in super supported setup and with a vertical load at the mid-span section. For sure, you will accept that we are going to find maximum tensile stresses at the bottom edge and compression at the top. This is true in cold conditions, but totally different in fire conditions. So where we have an heating source and an increase in temperature in the time of analysis. The reason is just related to the degradation of Young modulus with temperature, something that we can easily justify in the form of bending stiffness modification as a function of temperature, so exposure time, and for sure we can associate to a transition, migration of stress peaks to other regions of our beam. And this is very simple to see because here we have the mid-span section. So it happens that after 10 minutes, we are more or less at 5 millimeters of deflection. The effects of fire can be still disregarded, and you can see a very small layer in the bottom, which is white, so representing glass material which is no more able to carry on the mechanical loads. After 20 minutes, we have a maximum deflection in the order of 7 or 8 millimeters, but a totally different configuration if you look at the principal stresses in glass. Again, the white region represents glass material with residual bending capacity against the mechanical loads. But if you look at the portion in white compared to the total size of the beam, you can also understand the reason of an increasing deflection even in presence of constant mechanical load on the top. So what happens from 0 to 50 minutes is just to keep a very small weight on the top of the beam and increase the temperature on the bottom. The beam, after 40 minutes of exposure, is going to experience more or less 15 millimeters of deflection, but you can see that is able to sustain mechanical loads in the portions of glass that are protected from fire only. So those portions where we did introduce the insulation panel to avoid very high temperature increase. The problem is even more complex because if we look at the temperature evolution and distribution through the thickness of our resisting section, you can see something like this from 1 minute of exposure up to 60 minutes. Temperature, for sure, is not uniform in the height of the section, but also in the thickness. And so this is the reason of, let's say, unsymmetrical and non-uniform stress peaks in glass. And you can see again the detail. So what happens if we take into account the three performance indicators, and we start from maximum stress. For sure, it happens that we cannot expect anymore that tensile stress peaks are representative of the bending behavior at the bottom edge of mid-span section. This is something that we can do in cold conditions only. But for sure, if you look at the other control points, P2 and P3, you will see that our tensile resistance is first exceeded compared to P1, just because of the modification of Young modulus and so modification of bending stiffness. You can see also what happens in the chart on the right, what happens if we take track of, let's say, the loading condition leading to stress fracture in glass when we use different glass types, so annealed, heat strengthened, and fully tempered. You will see that there is no proportionality of our resisting domain. So we are talking about the limit condition in which we can sustain both the mechanical and thermal loads compared to the actual mechanical resistance of glass. There is no more proportionality. We did talk about 45, 70, and 120 megapascal for these three solutions, but you can see a totally different evolution, just because of the complex effect that governs the thermomechanical response of the system. Okay, so let's try to check the fire performance in terms of deformation and no more maximum stresses. And our reference is the conventional deformation limit that we can find in standards for simply supported beams in fire conditions. What happens when we try to check this failure limit against different magnitudes of vertical load in fire? It happens more or less that the failure condition is, let's say, simultaneous for all of them. So this means that the mechanical load has a very small effect compared to fire if we want to apply a conventional deformation limit to our beams. Just imagine that we are talking about 8.7 or 8.8 minutes of exposure capacity, which is very big compared to the stress check, where our reference was in the order of 2 to 5 minutes of exposure. So let's try to check what happens in terms of deformation rate and no more deformation only. Also in this case, we take a reference limit value from standards. What happens again is that we cannot see strong modifications in the deformation rate as a function of exposure time, even when we did increase the mechanical load at midspan. But okay, what can we say as a general conclusion for deformation rate parameters? We can say that okay, the effect of glass type, you can see annealed compared to heat strengthened, has a very small effect for the global, let's say, deformation analysis. But if we go back to the local performance indicators of these solutions, we can still find some modifications. And these modifications are again different from stress indicators. So at this stage, what we are trying to do is to find a general discussion and general performance indicators to take care of this resistance assessment in fire conditions. But okay, we must also say that we did talk about the monolithic glass section, and this is not representative of real applications. This is true. So let's try to do again the same study, at least for stress analysis, in terms of laminated glass sections. As you can see, the red curve is the monolithic one with identical size. The blue one is a double laminated section with 2 glass layers. We have then the laminated section with 4 glass layers, and finally the section with 6 glass layers. Why the reason of this comparison? The reason is that in cold conditions, we assume, and this is easy to justify, that increasing the number of glass layers, we are going to increase the bending stiffness and the resisting surface of glass against the mechanical loads. So the increase of benefits for the resistance design check is more or less proportional to the number of layers, moving from the simple monolithic to a big number of glass components. But in fire conditions, we did see that the configuration is totally different because of the progressive bending stiffness degradation and because of the transition of stress peaks from the bottom midspan edge region towards the section, the region of, let's say, top corner, towards the cold region of glass. So what happens again if we check the first stress value, which can suggest for us the fracture collapse of the beam? It happens that you can easily see from this chart, there is no more a linear proportionality between the number of layers and between, let's say, the loading configuration. And this is true especially when we have, let's say, a very big mechanical load for the section to verify. So a mechanical load which gives us a tensile stress in the bottom very close to the resistance of the basic material in combination with fire. For this reason, you can see that some of the dots are overlapped. For example, LG4 and LG6 are mostly identical in presence of fire only because of F equal to 0. This means that the effect of bending stiffness modification due to temperature only is so strong, even for 4 or 6 glass layers, that okay, our maximum stress peaks are still related to the region in the top corner, like in these contour plots. This is something totally different from cold analysis. But okay, you will also recognize that it is a complex problem to solve because we can no more take into account only mechanical aspects of this new material for buildings, but the specific combination of these mechanical properties and the intrinsic features of glass material together with its modification with temperature as it happens in fire conditions. So for sure, we did explore today only some aspects of this complex behavior, but I think, okay, we have more or less a clear way how to go on, especially with the support of experimental results that nowadays are increasing in the literature for this specific material and application. The most important aspect at this stage is that we cannot draw general conclusions that are extended from designing cold conditions only, and for sure this kind of research projects will allow to develop some for sure simplified but more general tools and concepts to guide designers in this new material and new applications for buildings. So at this stage, I would like to thank you for the attention, and I hope you will find interesting this kind of discussion.
Cool.
Thank you, Chiara. Yeah. Hello, Matt. Sorry,
Yeah,
you go.
thank you very much for your presentation. Yeah, we appreciate you coming and giving this. If people have any questions, please post them in the Q&A. To start them going, I guess. I will admit, I have never done any stress or mechanical analysis in my life, as I'm trained as a physicist, so I found that pretty difficult to follow as a whole. But so hopefully my questions aren't too stupid. But I was curious. This model. So the model you were designing, is that intended? I wasn't quite clear on the applications. Is that intended to be used like by designers to help them design better structural glass, or to help them plan for how the glass they have is going to behave in fire, or is it just like to help you understand what's going on in the glass? I couldn't quite understand which one it was.
Well, I can say it is both the aspects, because on one side you must take into account that there are a lot of applications made of traditional glass nowadays, which do not account for possible fire conditions. So are we sure we can still use them, or do we need to replace with something different in buildings? And probably it will be not of interest for industrial applications, because there we have already special glass solutions, but this is the case of ordinary buildings, our homes and offices, and go on. So if we are able to take control of this performance and material modifications, probably we can also avoid some troubles in the post-design stage and improve the structural behavior even in fine conditions for the full day design life of these members.
Cool, great. And we got a question here from Tatenda. Thank you for this, Tatenda. He was asking, how did you determine the temperature-dependent properties for the glass that you used in your model? So
yeah, I did use values from literature. So everything you did see, or you can find also in some publications, is taken from experimental studies. I must confess that it was very difficult to find this data, because one of them is from the 60s, so a very old paper, and one of the few documents where you can easily find a discussion of the modification of mechanical properties of glass with high temperature. So I think that it would be nice also to have additional experiments, not only on structural assemblies, but also on the material itself, because actually we are still doing experiments for material characterization also in cold conditions. So you must imagine what happens in fire, even more uncertainty and complexity to solve.
yeah.
Yeah, I would like to say one thing here. So firstly, thank you very much for this talk. It was really amazing, and I'm going to definitely be looking into the paper that you have referenced. I've been looking into glass, and I agree that material properties are something really hard to find. Not only the mechanical properties, but I found it also very hard to find thermal properties of glass used for construction. So, for example, values for emissivity, transmittivity, and reflectivity, that was really hard to find anything published on these values. I don't know if you've had the same issue and if you have something to suggest. Also, when you start adding the interlayer, it gets even more complicated. And I wanted to ask you if in your experiments, I think you did some experiments with PVB interlayer. What happened to the interlayer? Did you see, did it always behave in the same way? Did you see it? I've read on some paper that you can see it bubbling. Did you see something like that, or maybe does it happen that delamination occurs? Maybe the layers detach from one another. What was your observation regarding the interlayer?
Well, for sure, in fire conditions, you cannot take into account any contribution from the interlayer, especially under in plane bending, because you start already in a region close to zero contribution for glass, and so the high temperature is going to melt your layers. What I did see, sorry.
Is there like a temperature at which the interlayer starts not having an effect, or do you just disregard it from a very low temperature?
Yeah, if you use PVB, for example, your shear stiffness is close to zero, more or less at 40-50 degrees. So you don't need to expect a fire event to have more or less a new stiffness contribution. But in another project, I had the opportunity to follow some different experiments. So just imagine again a double laminated section, and it was not in a vertical position but horizontal one. So under heating process and then bending in cold condition, what we did see was that high temperature was going to reduce to zero the contribution of PVB. But given that we did run the bending experiment after few minutes after the end of the heating process, we did see that PVB was cooling down again and was able to take care of some of the mechanical load. But in this case, it was a particular condition because temperature was not so high like in a real fire accident. And so I'm not sure that this would be possible in accidental events or at least in the very first minutes of exposure. There are also special interlayers for fire-resistant glass. So this is another important aspect when we do talk about fire-resistant glass. So not the traditional glass. We have a special laminated glass sections in which forms and other particular interlayers, but it is more or less impossible to obtain the mechanical and thermal properties of these materials. And their effect is to stop temperature spread and to postpone the heating process for the section. But actually, you can try. I think if you're able to find some material parameters, please write me because I'm looking for them.
Yeah, we're on the same boat. So if there's not any question in the Q&A, I'll ask you another question. Thank you for your response, by the way. So I think in your experiments, you heated the glass beam using a furnace and following the standard temperature time curve, correct? Yeah. Do you know, so the temperature time curve is heats up, it has a really rapid increase in temperature from the start, so very like a very large change in temperature in a small time. Do you know what would be effect if you had a slower heating rate? So if the heat, the temperature of the beam is increasing quite slowly. Do you ever explore this?
Well, the risk could be, okay, on one side I would expect an improved performance, so failure time for the final collapse of the beam. But on the other side, the risk is a possible thermal shock for glass, which is something, again, related to temperature that we didn't talk about it today, and is representative of too big thermal gradient in the portions of glass that are hot and cold. And you can find this effect also in window panels, for example, in the region of supporting frames, where the effect of very fast transition from high temperature to cold result in a fracture of glass even without fire. So probably the risk of slow temperature increase even in fire could be something like this. So you can see that it's a very complex material, and well, there are several aspects that still need to be solved in support of design.
Definitely. So there's a lot of work to do. Matt, do you have any question that you would like to add? We are a bit over time. We need to start wrapping up.
No, that's okay. I'm
okay.
Good. Thank you very much, Chiara, for the presentation.
Thank you for this event, and see you next time. I don't know, everywhere, depending on.
Hopefully, yeah.
Yeah.
This talk will also be uploaded on our website. So if you agree, so people will be able to rewatch this talk or watch it if they weren't able to attend. So you might get some question later on when people do get the chance to actually watch this recording.
Mm-hmm.
Yeah, we want to thank you for taking some time and talking to us.